All right, so what are you trying to figure out in this problem? Looks like the first part is just asking, yeah, we could take a look at that one next. Looks like this first part is just asking what's the tension in the chain here. So we need to figure out how much tension force there is in this chain. Based on that, and later we're also going to want to find the force on the force of the hinge. Based on that concept that we're trying to find the force in the chain and the force in the hinge, what's the one big object we should really be considering here? What object are all these forces acting on? Yeah, the drawbridge itself. So we want to treat the drawbridge as the object in question. So we've got this drawbridge. And what forces are acting on it? Yeah, we definitely have gravity, which we should assume is presumably located in the center. Let me make that a little smaller. Force of gravity located in the center. We've got a force of tension at the location of the chain and in the direction of the chain. Tension is always in the direction of the rope or chain or whatever. And yeah, also a force from the pivot. The thing is, we don't even know which direction the force from the pivot point is in. So I'm just going to say there's some unknown force. And let me mark the pivot point as well. Pivot point is the hinge itself. So there's our pivot point. So we're going to have force of gravity, force of tension, and force of the pivot. And we don't know anything at all about the force of the pivot. We don't even know the direction it's pointing. So I'm not even going to put in an arrow for that yet. That's just unknown. Force of tension, we don't know how strong it is, but we at least know which direction it's pointing. Pointing in the direction of the chain itself. And how strong should we expect gravity to be here? Yeah, it should be 8,000 newtons because the mass of the drawbridge is 800 kilograms. Force of gravity should be mass times acceleration of gravity. Mass is 800 kilograms. We're treating g as approximately 10 meters per second squared. 800 times 10 would be 8,000 newtons. So that will be the force of gravity on the drawbridge. So it looks like that's all the forces we're dealing with. And let me take that off to the side to avoid some clutter here. So there's our diagram. We have this object, this pivot point, three forces acting on it. And based on that information, we want to figure out, first of all, how strong is the force of tension? And what do we know about all these forces? Normal force comes from when an object is in contact with another object, if you've got these two surfaces pushing on each other. In this case, what are the only other objects the drawbridge is in contact with? The tower itself, and we're taking that into account with the tension force from the chain that connects it to the tower, and also the force from the pivot. So the force from the pivot, the force from this hinge here, is presumably at least partly a normal force. It's presumably going to be some combination of normal force and maybe friction force as well. But the thing is, we don't really need to know what type of force it is, whether it counts as normal force or friction force or whatever, just that the pivot point, the hinge itself, is exerting some amount of force. So the normal force in this case is sort of incorporated into this unknown pivot force. Technically, I guess we could say the pivot force is going to have a component perpendicular to the wall, which we would call a normal force, and a component parallel to the wall, which we might call a friction force. But in general, we could just call it the pivot force or the hinge force. On the other hand, if the drawbridge were like resting on the ground or something, then there would be a normal force from the ground, but it's not in this case. Any other questions on that diagram so far? How is there a pivot force? The pivot is the hinge itself where the drawbridge is connected to the wall. And the thing is, if that wasn't there, if the only forces were the tension force and the gravity force, those forces wouldn't be able to cancel out. The tension force, if you consider this as split into horizontal and vertical components, it's possible that the vertical component of tension might cancel out gravity, but the horizontal component would have nothing to cancel it out. So if tension and gravity were the only forces, then the forces could not possibly add up to zero, which means the drawbridge is going to accelerate. The fact that the drawbridge is not accelerating means there's some other force holding it in place, and that other force is from the hinge itself. So the hinge is just providing whatever other force is necessary to keep this object rooted in place. And that's typically what a hinge or a fulcrum or a pivot point in general does. The pivot is going to provide whatever force is needed to keep this object from accelerating, making everything add up to zero. In fact, we can write that out as an equation, that the sum of the forces has to add up to zero. And since this is a two-dimensional situation, we can actually split that into two equations. The sum of the x components of the forces adds up to zero, and separately, the sum of the y components of the forces adds up to zero. So we've got two equations there. Problem is, though, how many unknowns do we have? Two unknowns, and what are those two unknowns? Yeah, we don't know the force of tension, we don't know the pivot force, although technically the pivot force is two unknowns in its own right, because for the pivot force, we don't know the magnitude and we don't know the direction. So there's really three unknowns. We don't know how strong the tension force is, we don't know how strong the pivot force is, and we don't know in which direction the pivot force is. So that's too many unknowns. We've got three unknowns: tension magnitude, pivot force magnitude, and pivot force direction. The tension force is split in, if we think of this as x and y components, we got unknown x and y components for the pivot force and unknown x and y components for the tension force. But we at least know the direction of the tension force. So we could establish another equation describing how the tension's x and y components are related to each other. So you could consider this four unknowns: F pivot x, F pivot y, F tension x, F tension y. But our equations would be the x components add up to zero and the y components add up to zero. And you could establish another equation using trigonometry to figure out how the x and y components of tension are related to each other. But either way, we're going to need one more equation. So what else do we know here? If this object is just staying still, what other equation can we always set up? Yeah, the torques have to add up to zero. So we can set up a fourth equation or third equation, depending on your point of view, saying that the torques have to add up to zero. So if we take torque and we say that the sum of the torques is zero, this is actually a very useful equation to start with, because if we set up torques instead, and really we need to analyze all of these equations. To figure out everything, we need to know that the torques add up to zero and the x components of force add up to zero and the y components of force add up to zero. But if we start with the torque equation, if we're just looking at torque, what can we ignore? Yeah, the pivot force is going to exert no torque at all. This is one of the really useful things about the torque equation. If we're looking at just torque, any force at the pivot point, it still counts as a force, but it does not count as torque. We just have, in this case, torque from tension and torque from gravity adding up to zero. And why is that? Why can we ignore the force from the pivot here when we're looking at torque? Yeah, the radius is zero. Generally, the torque is force times radius times sine of the angle, Or you could write it as force perpendicular times radius, or as force times perpendicular component of radius. But either way, if the radius is 0, then you get no torque. And the force of the hinge force here is located at the pivot point. So the radius, the distance from the pivot point to the force, is 0. In fact, that's going to be true of any force at the pivot point. Whatever point you choose to call the pivot point, any force acting at that point creates no torque at all. So this makes the torque equation much easier to deal with. If you choose a pivot point that's the location of some force you'd rather not have to care about, then that force creates no torque. So we just have to deal with, in this case, torque from tension and torque from gravity. And if you've got two things that add up to 0, what has to be true about those two things? Yeah, one of them is just the negative of the other. Torque from tension is the exact opposite of torque from gravity. In other words, they're the same magnitude, but opposite direction. We can establish that they're opposite direction using the right-hand rule. Like, for instance, torque from gravity is going to be into the screen. Torque from tension is going to be, tension is going to be out of the screen. So we can establish that they're in opposite directions using the right-hand rule. Formally, we could assign a positive to one of them and a negative to the other one. But if there's just two things that add up to 0, and we've already established they're in opposite directions, we can just say their magnitudes are equal. Magnitude of torque from tension equals magnitude of torque from gravity. And then to calculate those torques, there's a few ways we could do this. We could split them into components, not the usual x and y components, but instead parallel and perpendicular components, and use F perpendicular times R. Or we could write it as the entire force times the entire radius times sine of the angle between them. Which one of those formulas do you want to try using here? How do you want to write out the torque? Yeah, let's try the perpendicular stuff, the F perpendicular times R. Because the F times R times sine theta, you just take the entire force, in this case, let's say 8,000 for gravity, times the entire radius, the length from pivot to the location, times the sine of the angle between them. So you need to find that angle. And in this case, what would be that angle? If we wanted to know the angle between the radius vector, yeah, that angle should be 30 degrees. We've got our radius vector here, which in this case is just half of the length, so that'll be 3 meters. So for gravity, R is 3 meters. And the angle we're talking about is this angle. And since we've got a 60-degree angle here with the horizontal, the angle made with the vertical is going to be 30 degrees. So that should be a 30-degree angle. So we could use R times F times sine theta, which is just going to be 3 meters times 8,000 times sine of 30. Let me make a note of that, and then we'll take a look at how we do this using F perpendicular times R instead. So we should expect torque from gravity is going to be R times force times sine of 30 degrees. And sine of 30, I think, is 1/2. So this should just be 3 times 8,000 times 1/2, which is 12,000. So we should expect 12,000 Newton meters. But let's try doing this using the other method, using the idea of splitting this into perpendicular and parallel components. The idea is we want to rewrite the force of gravity in terms of its components, not the usual x and y components, horizontal and vertical, because it's already purely vertical anyway. Instead, we want to split this into a component perpendicular to the drawbridge itself, perpendicular to the radius vector, and a component parallel to the radius vector. And let me adjust those. because ideally we want to create a new right triangle with the vector itself as the hypotenuse, and the other sides having one side perpendicular to the drawbridge, the radius vector, and the other side parallel to the drawbridge. So this triangle will split up the force of gravity, 8,000 newtons as the hypotenuse, into a perpendicular component, which is what we actually care about, and a parallel component, which we don't really care about. Parallel in the sense of parallel to the drawbridge itself. So what we want to do is we want to find the perpendicular component. And to do that, we're going to need at least one of the acute angles in this triangle. We know we've got a right angle here by definition. Can you find either one of these other angles in the triangle, though? Yeah, it looks like these two angles are right angles, or complementary. They form a right angle. So this is going to have to be 60 degrees. So we could say the perpendicular component is found using cosine of 60. Or alternatively, what's this other angle going to be? Yeah, that's going to have to be 30 because those angles have to add up to 90. You could also look at that in terms of if you've got a line and another line that's parallel to it. Those don't really look parallel. Let me fix that. If you've got two parallel lines and another line passing through both of them, then what we've just formed is alternate interior angles. Those two angles have to be parallel because those lines are, or have to be congruent because those lines are parallel. So by creating a parallel line, parallel to the drawbridge itself, and having gravity be another line cutting through those parallel lines, we created alternate interior angles that have to be congruent. Any questions on the angles there so far? Okay. So we've established this 30-degree angle here, and you could use the 60-degree angle or the 30-degree angle. I would generally find it preferable to use the 30-degree angle here, just because that way we can make use of the same information we already had. In many cases, it's a good idea to make use, to most directly make use of information that's already given in the problem, information you know for sure. Because if you use information that you built off of previous information, the more steps that it takes to get from one place to the next, the more opportunities there are for something to go wrong. In an ideal world, if you're absolutely certain that you haven't made any mistakes at all, you can use any of this information. But it's often a good idea to use information you know for certain whenever possible, because that way you're reducing the chance of making a mistake. So with this 30-degree angle, how would we find the perpendicular component? If we know that the hypotenuse, the magnitude of the vector itself, is 8,000 newtons, how do we find the perpendicular component? Yeah, sine should work here because the perpendicular component is opposite from the 30-degree angle. So we could say that's 8,000 newtons times sine of 30 degrees. You could alternatively say it's 8,000 newtons times cosine of 60 degrees because this is adjacent to the 60-degree angle. But again, I think it would be preferable to use the 30-degree angle because that's most directly related to what we already got here. So 8,000 newtons times sine 30. Also note that that matches up with the 8,000 newtons times sine 30 that we were doing earlier with just the r times f times sine theta definition of torque. So this is still going to get the same result. We can say that torque from gravity equals R times F perpendicular, which is 3 meters times 8,000 newtons times sine 30. Either way, we get the same thing. R times F times sine theta is the same as R times F perpendicular. Any questions on that so far? And sine 30, I think, is just 1/2. So that means we're going to get 8,000 times 1/2, which is just 4,000. So the perpendicular component of gravity is 4,000. And for torque, that's all we're going to need. In the second part of the problem, though, I think we're going to need the parallel component as well. Because for part 2, it's asking specifically to find the force on the hinge using the coordinate system given in the figure. And the coordinate system provided here is assuming that the x coordinate is parallel to the drawbridge and the y component is perpendicular to the drawbridge. So let's go ahead and just treat that as our new xy coordinate system. Perpendicular component, which is the y component, is 4,000. And what would we do to find the parallel component, the new x component? If we want to know this adjacent side, yeah, we'd use cosine. So we take the same 8,000 Newton hypotenuse, multiply it by cosine of 30, because it's adjacent to that angle. And we get 8,000 times root 3 over 2. So that's 2,000, 4,000 root 3. About 6,928. So that would be the parallel component. In other words, we can say that gravity, written in terms of components, force of gravity is 6,928 newtons in the x direction and 4,000 newtons in the y direction. Not the usual horizontal vertical xy, but instead this tilted coordinate system, which is what it suggests to use in part B. Any questions on those components so far? In this case, yeah, I think those would be negative because the direction the arrows are pointing in this diagram, I would interpret as the positive x direction and the negative x direction. And since gravity is down and to the right in the y direction, we would treat that as negative. And then down and to the left in the x direction, we're going to treat that as negative as well. So yeah, based on the diagram as shown here, I would treat those as negative 6,928 and negative 4,000. So those are the xy components in this new coordinate system. And with that, I think we have all the information we need to work out torque. Torque from tension is going to be the force times the radius. Also, what's the angle between this radius and this force for tension? Yeah, the drawbridge and the force of tension, the chain, make a 90-degree angle as shown in the original diagram. So in that case, we can just say force of tension times radius times sine of 90, and sine of 90 is 1. So that will be torque from tension. We've got radius. What is the radius for the chain? How far is the chain from the pivot point? Yeah, 6 meters, the full length of the drawbridge, times this unknown force of tension times sine of 90, which is just 1, equals torque from gravity, which we found earlier was this value, 3 meters times 8,000 newtons times sine 30. So that's 6 meters times unknown force of tension times 1 equals 3 times 8,000 times sine 30, which we found earlier was 12,000. And then what else do we still need to do to find a force of tension? Yeah, divide by 6 meters. We get force of tension is 12,000 over 6 would be 2,000. Meters cancel out, so we get newtons. So that is the force of tension, 2,000 newtons. Another important thing to note here, the chain is how far away from the pivot compared to gravity. What's the ratio of distances there? Yeah, the chain is twice as far away. How do the forces compare? It's a fourth as much in terms of the total force. But for tension, for torque, we should just be looking at the perpendicular component of the force, right? If we take a look at the tension, which is all perpendicular, and compare it to just the perpendicular component of gravity, how do those forces compare? Yeah, half as much. So we shouldn't really be looking at the actual force. We should be looking at just the perpendicular component of the force. The chain is twice as far away, so it only needs half as much as the perpendicular component of gravity, half as much force. Twice as far away means half as much perpendicular force. The parallel force doesn't matter.
Casey, I have a question.
Yeah, go ahead.
Where did you get the sine 90, where it's like 6 meters times force of tension? Why do we need the sine 90? I thought it was just like R times F perp.
Yeah, we could write it that way as well. We could say R times the perpendicular component of force. R is 6 meters. And since the tension force is perpendicular, the 2,000 newtons is all perpendicular component. You could also write it as the total force, which is, or the entire force of tension, which is 2,000 newtons, times the radius, which is 6 meters, times sine of the 90-degree angle. But sine of 90 degrees is 1, so that means it doesn't actually influence the result.
All right, yeah, thank you.
Either way, you get the same thing. And that's one of the things I'm trying to emphasize here, that all three of these formulas are really just the same formula, just written in different ways. That you could say 2,000 newtons times the 6 meters times sine of 90, or since the force is entirely perpendicular, you could ignore the angle entirely. Either way, you get the same result. In fact, now that we know that, we can write the tension force in terms of its components. We can say the force of tension is 0 in the x direction, because there's no parallel component at all, and 2,000 in the positive y direction. So in the same way that we wrote the force of gravity in terms of its new x and y components, we can also write the force of tension in terms of new x and y components, new in the sense of using this new tilted coordinate system. So tension is 0, 2,000 because it's 2,000 in the perpendicular direction and none at all in the parallel direction. Any questions on that so far? And now to answer part B, we can go back to our original assumption that the x components of the forces add up to 0, and separately the y components of the forces add up to 0. But instead of using the conventional vertical and horizontal, we're going to use our new diagonal tilted coordinate system, as shown in the diagram. So based on that new coordinate system, what forces have x components here? Yeah, gravity has an x component because we're treating x as parallel to the bridge. And yeah, the hinge itself could have an x component, presumably does have an x component. But in general, you should assume that an unknown force could have components in all directions unless you know for sure that it doesn't. So let's say force of the pivot in the x direction plus force of gravity in the x direction equals 0. Force of the pivot in the x direction is unknown, but we know the force of gravity in the x direction is negative 6,928. And so we can solve for FPX just by adding that to both sides. So there's the x component. What about for the y component? What forces have y components here? Yeah, all of them have y components. So we're going to need to include pivot force y component, gravity force y component, and tension y component, and say those all add up to 0. Pivot is still unknown. Gravity, though, we know is 4,000 in the negative y direction, so that's negative 4,000 newtons. And tension, its y component is positive 2,000. So that should be our y equation. Y component of pivot minus 4,000 from gravity plus 2,000 from the tension equals 0. And then that combines to just negative 4,000 or negative 2,000. Add 2,000 to both sides, and we now have the y component. Combine those, and we get force of the pivot is x component, comma, y component. So we now know the x and y components of the force of the pivot in the new coordinate system. Any questions on that so far? And if we wanted to find the magnitude, what would we do? How could we convert the x and y components into a magnitude?
Pythagorean theorem.
Yeah, we use our usual Pythagorean theorem. Magnitude of the pivot force is going to be square root of x component squared plus y component squared. Order doesn't matter. So we punch that into a calculator, Pythagorize that, and we get 7,211. So that is how strong the pivot force is. The pivot force magnitude is 7,211 newtons, almost as strong as the weight of the bridge itself. And also, what about direction? How can we convert this into a direction? Yeah, we can use an inverse tangent. And I think it's going to be helpful here to draw out a diagram just to get more of a feel for which direction this is actually going. Because we are using an unusual coordinate system. What we have here is a force that is in the x direction and y direction in this new coordinate system. So that is 6,928 in the x direction and 2,000 in the y direction. So about a third of that, something like that. So we're going to have those values. We have 6,928 and 2,000. And what we're actually looking for is this vector. So when we take the inverse tangent, we're actually going to be finding this missing angle. So let's try that inverse tangent. We can say that this angle is tangent, or tangent of this angle is opposite over adjacent, 2,000 over 6,928. So we take the inverse tangent of that. And let's see what we get. Inverse tangent, 2,000 over 6,928, about 16 degrees. So that means the force of the hinge is 16 degrees elevated from the drawbridge itself. Alternatively, if we wanted to give that as an angle from horizontal, how would we find the angle from horizontal? If we wanted to know this angle. Yeah, we can just add 60. So we can say that the pivot force, we certainly know the magnitude is 7,211 newtons. For the direction, we can say that it is 16 degrees above the drawbridge itself, or we could say 76 degrees above horizontal. Either way works, as long as that's just describing the direction of the force. Any other questions on that? Why isn't it 30? Oh, it's not quite a right angle, actually. We shouldn't assume that anything about the direction of this. The pivot force is not straight up. In fact, I wasn't really drawing this to scale. It should really be much more like this, I think. Something like that. So don't assume that something is automatically straight up or straight sideways or something just because it kind of looks like it. In this case, it really turns out to be more like this. The important thing is to trust the numbers, I think. That you should certainly don't ignore the intuitive idea of what it looks like, but don't trust it too much either. That don't assume something is perfectly vertical or perfectly horizontal just because it kind of looks like it in the diagram. In this case, it turns out it is very much not vertical. Any other questions on that? All right, then let's see what else we can do. Someone was asking about question 2B from the practice final on the website. Let me pull that up. There it is. All right, so in this one, we are looking at a hose. So this is some information from the fluid flow stuff, but we're also combining it with the kinematic stuff from more recently. That we're looking at the shaded portions of this hose, these little gray rectangles. These little gray blobs are supposed to represent one little chunk of water. And we want to figure out, as it moves around, what's the direction of the net force on that little chunk of water at that location. And for that, to figure out the force on each blob of water, what does force do to an object? Yeah, force causes acceleration. Specifically, force equals mass times acceleration. Force and acceleration are vectors. So if we want to figure out the direction of the force, if any, we need to do so by figuring out the direction of the acceleration, if any. So let's take a look at each of these locations. Let's start by focusing on, let me just label these as, let's say, location 1, location 2, and location 3. So starting at location 1. At location 1, what would you expect this blob of water to be doing as it moves? Is there any acceleration going on there? No, and why is that? If you think back to what you learned about fluid flow at the beginning of the quarter, why would you expect this blob of water to be not accelerating as it moves? Right, no change in area. From the continuity principle from way back at the beginning of the quarter, if the only way that the speed of a fluid in a pipe can change from location to location is if the area changes. So for instance, at location 3, we're going to want to consider that. We've got an area changing from location to location. So at location 3, we would need to consider a change in speed. Yeah, we can take a look at number 8 later as well. But at location 1, there's no change in cross-sectional area. This blob of water is just moving in a straight line at constant speed. So at location 1, we've got no acceleration, and therefore no force. So at location 1, we should expect this blob of water to be experiencing a total force of 0. it is experiencing forces. It's being pushed forward by the water behind it and being pushed backwards by the water in front of it and being pushed inwards from the walls of the pipe on all sides. And maybe there's even gravity involved. But all those forces cancel each other out. The total force on this plug of water is 0. Constant velocity means no acceleration. Constant speed does not mean no acceleration, though, because speed means how fast it's going, but does not take direction into account. And that actually becomes important at location 2, because what's happening to the blob of water at location 2? It is changing direction, yeah, which means the velocity is not constant. The speed is constant. As the object is turning the corner, there's no changes in cross-sectional area, so the speed is the same. It's going at the same speed the whole time, but it's changing the direction of travel. So that means that the velocity is not the same. The speed is the same. It's still traveling at the same rate in terms of meters per second. But the fact that it has changed direction means that there is an acceleration. The water is accelerating because it's changing direction. In fact, we could even treat this as circular motion. During that period of time, the object is traveling on what we can consider a circular path. Let me see if I can get this right. Or pretty close to circular anyway. We can treat this curve as a portion of a circular path. Maybe smaller. So something like that. So treating it as this portion of a circular path, anytime you've got an object moving on a circular path at constant speed, it is experiencing a force making it change direction. Because with no force, it would just keep going in a straight line. And which direction does that force have to be if you got an object moving in a circular path? If you got this object moving on a curved path, yeah, you have to have a force towards the center of the circle, a centripetal force. In fact, you can even see that based on, if you just compare, let's say, the initial and final velocity. Here's our initial velocity, here's our final velocity. The difference from initial to final is going to be the direction of the force. We've got our V initial, we've got our V final. Yeah, centripetal force, centripetal just means towards the center. That's all it means. It's just, I think, Latin, maybe Greek for towards the center. If you compare the starting velocity and the final velocity, at the beginning, it's moving upwards. At the end, it's moving to the right. So if you compare V initial and V final, let me make those more accurate. They should be the same length, same magnitude. So if you want to take the difference, if you want to take delta V is just final minus initial. It's the difference that takes you from the initial value to the final value. So delta V is going to be this difference vector. That's the change from initial to final velocity. And then the acceleration is just delta V over delta T. And then multiply both sides by mass, and you get force. So the force is going to be in the same direction as the change in velocity. In other words, in this case, down and to the right. And the reason we call that a centripetal acceleration or a centripetal force in the sense of the direction is that the path could be, that curved path here could be thought of as a portion of a circle. that the path that it's following is a portion of a circle, this quarter circle arc. And the delta velocity, and therefore the acceleration, and therefore the force, are pointing straight towards the center of the circle. I would say delta velocity and acceleration and force are all in the same direction, because force is proportional to acceleration, and acceleration is proportional to delta velocity. So force, acceleration, and delta velocity should all point in the same direction, which in this case is towards the center of the circle. And generally, anytime you've got uniform circular motion, that is an object moving on a path that's a circle or a portion of a circle and traveling at constant speed, not changing how fast it's going, then the acceleration, and therefore the total force, is always going to point towards the center of the circle. And we call that a centripetal acceleration or a centripetal force in terms of the direction. And keep in mind, centripetal isn't a type of force like tension or gravity or something. Centripetal is just a label for the direction. So we could say this force is in the centripetal direction. And presumably, again, there's lots of forces acting on this. There's the water behind it pushing forward, the water in front of it pushing back, the walls of the pipe pushing inwards, and maybe gravity as well. But the total of all those forces is towards the center of the circle. Presumably one wall of the pipe is pushing on it harder than the other wall is. So the total force is towards the center. Any other questions on location 2 so far? And then what's happening at location 3? As the pipe gets narrower at the nozzle, what's happening to this piece of water? Yeah, the velocity is increasing. It's getting faster and faster. So at location 3, the water is also accelerating. Because keep in mind, acceleration can mean several different things. Accelerating might mean it's changing how fast it's going, or accelerating might mean it's changing direction. So at location 2, we said the water was accelerating because it's changing direction. At location 3, we say the water is accelerating because it's changing speed. It's changing how fast it's traveling. And if it's getting faster and faster, which direction is that acceleration? If you've got an object, presumably the object is currently moving to the right, so its velocity is to the right now. Which direction does its acceleration have to be to make it get faster? Yeah, same direction as the velocity. So that's going to be to the right. So we should expect the acceleration here is to the right, and therefore the total force is also to the right. You can kind of see that by looking at velocity here. If you take a look at the velocity vectors, right before the nozzle, you're going to the right at some speed. After the nozzle, or later in the nozzle, you're going to the right at a faster speed. So we would have our initial velocity vector to the right, our final velocity vector to the right, but even more so. So if you compare those, if you want to take the difference, we could just put them at the same origin. So we've got our V initial, V final, and I find this a very useful way to subtract vectors. If you want to know the difference, put both vectors at the same origin, the same starting point, and look into what do you have to add to V initial to get to V final. So from the initial value to the final value, that's delta V. So delta V is to the right. And again, the acceleration and the net force are going to be in the same direction as that delta velocity. And in general, if you want an object to get faster, you need to apply a force in the same direction as its velocity already is. To make it get slower, you'd have to apply a force opposite to the velocity. And if all you want to do is change the direction, like at point 2, you apply a force perpendicular to the velocity. Like if you compare the force and the velocity here, at location 2, we had velocity, like exactly at location 2, velocity was up and to the right. So that was our velocity vector. In order to change the direction but not change the speed, we apply a force perpendicular to the velocity. So in general, if you've got velocity going one way and force pointing perfectly perpendicular to it, that's going to change the direction of travel but doesn't change the speed. On the other hand, if the velocity and the force are parallel, you're changing the speed but not changing the direction. And if the force is on some diagonal, it could be changing both the speed and the direction. Any questions on that so far? And one other thing on that subject, it's often useful to split up forces on a moving object into parallel and perpendicular components based on the velocity. Like let's say this is your velocity vector. If this is just the velocity right now of some object, and you're applying a force to it that's not perpendicular or parallel, but instead is on some diagonal. Let's say this is the force vector. In order to figure out what that does, it's a good idea to split up the force into components, not the usual X and Y components, but instead a parallel and perpendicular component. So I would split that into a component parallel to the velocity and a component perpendicular to the velocity. So we would label that as F perpendicular and F parallel. And if you look at those individually, what would the parallel component of the force alone do to the object? If we ignore the actual magnitude for now, yeah, the parallel component is going to increase the velocity, increase how fast it's traveling. So the parallel component of the force makes the object get faster and faster and faster. On the other hand, if we look at just the perpendicular component, what would a perpendicular force do? If you got a force that's exactly perpendicular to the velocity, what does that do to the object's motion? Yeah, that changes the direction. So by splitting the force into components, we can look at each piece individually. We can find the parallel component of the force, assuming we know this angle. We can find the parallel component of the force that tells us how fast the object is getting faster, how much the speed is changing per second. And taking a look at the perpendicular component of the force, that tells us the object's path is curving. So this diagonal force is going to make the object get faster and curve upwards. An exactly perpendicular force does not affect the magnitude of the velocity. Yeah, that it doesn't change how fast, if the force is perfectly perpendicular to the velocity and stays perpendicular, then that force does not change how fast the object is moving. It only changes what direction it's traveling. One common example of this is planets in orbit. If you've got a planet in orbit around the sun and the orbit is perfectly circular, the planet is traveling one way, but experiencing a force of gravity perpendicular to its velocity. So that means that the planet's speed does not change. It just changes which direction it's traveling. And of course, that's only true if the orbit is perfectly circular. If the orbit is not circular, if it's more elliptical, then that may make things different. But in a perfectly circular orbit, the planet's motion is in one direction and the force of gravity from the sun is perpendicular to that. Let me sketch that out real quick. Let's say this is the orbit, and then we have the sun at the center, and then we have a planet. So let's say at this instant in time, let's say the orbit is counterclockwise. So at this instant in time, the planet's velocity is this direction. The velocity is going to be tangential to the circular path. But what force is acting on the planet? If this planet's just floating around in space, presumably what's the only force acting on it? It should be in the perpendicular direction. What force is it? What's the gravitational force? And I would say the type of force is gravitational. We've got a gravitational force attracting the planet towards the sun. So this is force of gravity. The planet and the sun attract each other. And the direction is centripetal in the sense that it's towards the center of the circle. You could also describe that direction as perpendicular to the velocity of the planet. And so the reason the planet isn't just falling into the sun is because it's already in motion on this sideways direction. And the perpendicular component of the fact that the force is perpendicular means it's not changing how fast the planet is moving, it's just changing the direction of motion. So if we wait a little while, let's say we allow some time to pass. I can get hold of this. If we allow some time to pass, let's say the object is now here. At this point, its velocity has changed. It's now moving in this direction. It has changed direction, but it's not changing its speed. But also its force of gravity is still towards the sun. We're still going to have a force pulling the planet towards the sun. And note that the force of gravity is still perpendicular to the velocity. So this force of gravity from the sun is still acting as a perpendicular force, changing the direction of travel, but not changing the speed. And again, you could also think of that force of gravity as a centripetal force, which just maintains the circular motion. So the force of gravity isn't making the planet get closer to or further from the sun. It's just changing the direction in a continuous way that causes the planet to travel in a circular path instead of a straight line. And that only works if the planet is moving at a very specific velocity. If it's moving faster or slower, it's going to get an elliptical path rather than a circular path. Any other questions on that so far? Or on centripetal forces in general? All right, then let's take a 2 or 3 minute stretch break, and then we'll come back to the next problem that was requested in chat. All right, this one is the problem number 8 from that practice final on math.ncheese.org. Here we've got this outstretched arm and deltoid muscle attached 15 centimeters from the joint and pulling in this direction. We know the weight of the arm. We know where its center of mass is. We're trying to find the tangential component of the force from the muscle. So let's try drawing out a free body diagram there. What's the one object we really care about here? What's the object that all the important forces are acting on?
The arm?
Yeah, the arm itself. So we're going to treat the arm as the object we care about. We've got a variety of forces acting on it. First of all, though, we should probably establish a pivot point. What would you treat as the pivot point here?
The shoulder joint.
Yeah, the shoulder joint itself. In part because if this rotates, everything's going to be rotating around that point. And also, that's probably going to have some force there that we'd rather not have to worry about. So by treating the shoulder joint as the pivot, we know that any forces provided by the shoulder are going to have zero torque from that perspective. So what forces are acting on the arm here?
The weight of the arm.
Yeah, so that'll be a force of gravity. And we know that's 40 Newton. Where should we say that's located?
In the middle.
Yeah, and not necessarily the middle geometrically, but the center of mass, which we're told is 30 centimeters from the shoulder joint, as opposed to the muscle attachment point, which is 15 centimeters from the shoulder joint. So 15 centimeters, another 15 centimeters, that's where we should expect the force of gravity to be located. So that's force of gravity. And we know that is 40 newtons. We don't have to multiply by G because it's already a force. It's already given in newtons. If it had told us like the mass is 4 kilograms, we'd have to multiply by gravity. But if it tells us the weight as a force, that's already a force. It's already in newtons.
Casey, could you explain how you added 15 plus 15 centimeters? How did you know where to go?
Yeah, specifically that it tells us that the center of mass is 30 centimeters from the shoulder joint. So I should be placing this force of gravity exactly 30 centimeters away from the pivot. And just for a sense of scale, it tells us that the muscle is attached 15 centimeters from the shoulder joint. So we know that in terms of distances, we know that the distance from the pivot to the location where the muscle is attached is 15 centimeters. From the pivot to the location where gravity is active, that's 30 centimeters. So that should be twice as far as the distance from the pivot to the muscle. In fact, let me go ahead and label those while we're at it. We've got 30 centimeters here as the distance from the pivot to the center of mass versus 15 centimeters as the distance from the pivot point to the location where the muscle is attached. Any other forces we need to consider? What's preventing the arm from just dropping? Yeah, we've got a force from the pivot itself. And as usual, we don't even know which direction that's going to be in. So we just got some unknown pivot force. We don't even know the direction. So I'm just going to mark F pivot equals who knows. But the thing is, the pivot force itself does not exert any torque. So if all that's going on is gravity, the arm's just going to rotate. What's preventing the arm from dropping? What other organ has to be acting here to prevent the arm from falling? What's holding it up? Yeah, the muscle itself. So at that 15 centimeter location, we've got this diagonal force from the muscle pulling this way. And we don't know how strong that's going to be either. We've got some sort of muscle force, let's say F sub M. And we don't know how strong that is. but we at least know it's in some direction, this diagonal direction. And I think that should be the only forces involved here. There's no other, like the object, the arm isn't holding, you're not holding some weight in your hand, so there's no other forces there. Your arm isn't resting on a surface, so there's no normal force. There's no ropes or cables or chains involved, so no tension force other than the muscle itself. You could kind of treat the muscle as a tension force because the muscle is kind of acting like a cable pulling on the object. But these should be the only forces involved. Any questions on that diagram so far? So now that we've got that, I think it's safe to ignore the finer details of the bone structure and just look at this as just one rod-like object. And we want to know ultimately the tangential component of the force exerted by the muscle on the arm. This is kind of a weirdly worded question. The idea is that this problem, let me make this a little bigger for exaggeration. This problem doesn't really give us enough information to actually find the force of the muscle. In fact, if we wanted to find the force of the muscle, what other information do you think we would need to know?
We would need to know a few angles.
Yeah, we'd have to have at least some sort of angular information, some sort of information about what direction that actually is. The problem doesn't give us that information, so we can't actually find the force of the muscle. But it's not asking for the entire force of the muscle. It's just asking for the tangential component, tangential in the sense of perpendicular. So let's imagine splitting this into components. We could have, and so since it's a rotational thing, we typically want to split it up into a component perpendicular to the radius and a component parallel to the radius. Something like that. And we typically call the perpendicular component the tangential component also, in the sense that if this were to rotate, presumably it's going to rotate in a sort of a circular path. If we were to actually, like, let's say you take a look at this point. If you, let's say you put a mark on the arm at the location where the muscle attaches and you start rotating the arm. As the arm rotates, what path is that point going to trace out? If the arm starts rotating, what path would a single point on the arm trace out as it rotates?
I'm not sure if I'm answering it correctly, but like counterclockwise.
Well, not in terms of which direction, but just if it rotates, what shape does it make? It should just be a circle, yeah. If you put a mark on your arm and rotate your arm around, that point is tracing out a circle, or at least a portion of a circle. So if you actually draw out the circular path that that point traces out, it's going to look something like this-ish. The reason we call this the tangential component of the force, let me actually make that a little bigger as well. The reason we call this perpendicular component the tangential component is because it is tangent to that circle. So the circle, and you could also think of this as the circle traced out by that radius vector. We got a 15 centimeter radius vector, radius in the sense of the distance from the pivot point to the location where the force is applied. If you imagine spinning that radius vector around to make a circle, the perpendicular component is tangential to that circle, because any tangent line to a circle is guaranteed perpendicular to the radius vector. So the perpendicular component of the force is often called the tangential component. And then the parallel component is often called the radial component, in the sense that that component is parallel to the radius vector itself. So we've got a radial component of the force that is parallel to the radius vector, and a tangential component of the force, which is perpendicular to the radius vector, but tangential to the circle of motion. So that's the origin of this terminology. Tangential just means perpendicular to the radius. In other words, tangential to the circle itself. Any questions on those terms so far? So if we wanted to know what that tangential force is, how do you think these forces are related to each other? Is there any equation we can set up involving these unknown forces? If we know that the forearm is just staying still. Yeah, using torque would be good. We could use forces or torques. The forces have to add up to 0 and the torques have to add up to 0. But what would be the big advantage of using torque specifically? Yeah, if we're using torque, we can ignore any forces at the pivot point. And that's good because there's some unknown force at the pivot point that we'd rather not have to worry about. So let's use torque. Let's say we know that the sum of the torques has to be 0 because the arm, I should say, is not rotationally accelerating at all. It starts off at angular speed 0 and continues to have angular speed 0. So no rotational acceleration. And the only torques here are going to be torque from the muscle and torque from gravity. And again, if we had lots of torques, it would be a good idea to assign positive or negative to each one based on direction and the right-hand rule. But if you just have two things that add up to 0, you know they have to be equal and opposite. So you probably still want to check the right-hand rule just to make sure that they are opposite directions. Gravity inwards, and muscle inwards. Other way around, muscle outwards. But as long as they're opposite directions, their magnitudes just have to match. So magnitude of torque for the muscle has to equal magnitude of torque of gravity. And how would we write out each of those torques as a formula? Yeah, we could use RF sine theta, or alternatively, you could combine F sine theta to get what? Because I'm noticing we don't have any angles given here, so it would be better if we could not have to worry about the angles. Yeah, I'm just going to write each of those as R times F perpendicular. So R for the muscle times F perpendicular for the muscle equals R for gravity times F perpendicular for gravity. And F perpendicular is just the tangential component of the muscle force that we're looking for anyway. So if we fill these values in, we've got R for the muscle is 15 centimeters times F tangential that we're trying to find equals radius for gravity, that's 30 centimeters, times, and gravity is purely perpendicular to the radius already. So the perpendicular component is just the full force, 40 newtons. And then what else do we need to do to solve for F tangential? Yeah, divided by 15 centimeters. 30 over 15 is 2, and centimeters cancel out. So we get 80 newtons. And again, this is a proportionality thing. The muscle force is half as far, so it needs to be twice as strong. Yes, exactly. We don't need to convert centimeters to meters because the units cancel out anyway. The exact units you're using don't really matter very much. The important thing is just to have everything in the same units. And in this case, all the distances are in centimeters. So when we divide, they cancel out. Any other questions on that so far?
Yeah, I was going to ask, is there like because I've noticed this twice now, like what you're saying, that because the distance is proportional to the force that we're trying to find. So like, is there a universal shortcut? So like if the angle of the two forces is the same, then you can just take the factor of the radius?
Yeah, in this specific situation where you have only two forces that create torques, and let's assume that they're both perpendicular, or that you're looking at just the perpendicular components anyway. If you've got only two forces that are creating torques, and you know the torques have to balance out, then the ratio of or the product of radius times F perp and radius times F perp has to match. So let's explore that a little further. If you assume that torque 1 equals torque 2, then we can write, and let's assume for the moment that the forces are perpendicular, or that we're only looking at the perpendicular components anyway. Radius 1 times force 1 equals radius 2 times force 2. If you solve that for, let's say, force 2, what would you get?
R1 F1 over R2.
Right. In other words, F1 modified by the ratio R1 over R2. So the second force is the first force modified by that ratio. In this case, the radius, the radii, the distances are a ratio of 2 to 1. So the forces have to be a ratio of 1 to 2.
So does sine theta have to be the same though when we say this?
Either that, or you have to be looking at just the perpendicular components. Like here, we weren't looking at the actual muscle force at all. We were looking at just the perpendicular component of it.
Oh, so if they're perpendicular, then it doesn't, well, then it's given that the angle's the same, I guess, is kind of what.
Yeah.
Okay.
Yeah, here we're looking at just the perpendicular component.
So just, sorry, just as a hypothetical, so then like, if the only two forces acting on this were the FM pointing in that direction, and then there was just like another force with the same unknown angle with an opposite magnitude, could we find, and we knew what that magnitude was, could we then use the same thing? And it's like, well, because the distance is half.
Yeah, because if we did have a sine theta here and a sine theta here, if they were the same theta, then the sine theta 1 and sine theta 1 again would just cancel out anyway. In fact, we could even put that in here. We could say divide both sides by sine theta 1 or sine theta 2, and you get sine theta 2 1 over sine theta 2. So you could say that F2 is F1 modified by the ratio of distances and also modified by the ratio of sines of the angles. But if the angles are the same, those are going to cancel out anyway.
So for the angles to be the same, well, okay, so like just to use that example briefly, if there's a force that's the opposite direction as FM but the same magnitude, aren't those different angles though? If they're
well, the same angle made with the radius. So like if we had, let's say the force of gravity were this way instead. Like instead of gravity, let's say we had some other force. The angle we'd be considering would be this angle. As long as that's the same as this angle, then the sine thetas would cancel out.
Oh, okay. Okay, that makes sense.
So it doesn't, same angle doesn't have to mean same absolute direction. It just means same angle as measured from the radius, from the beam itself. Any other questions on that one? And then I think part B is pretty much just what we've already done, make an extended force diagram. If we want to make it roughly to scale though, we know the tangential component of the muscle force should be twice as large as the force of gravity, partly because we found 80 newtons when we calculated it, but also half as far should mean twice as strong. So let's adjust that to be more like the right size. I can grab all these at once. Okay, so we want the tangential component to be twice as large, so something like that. So it should actually be more like this. The muscle force is tremendously strong here because it's got to provide a perpendicular component that's twice as much as the force of gravity. And this is generally true. The force of the muscle is typically going to be much stronger than the load force that it's supporting, partly because you're losing the parallel component. You're only getting the perpendicular component as useful force, useful torque. And also because the muscle is attached close to the joint. You could have a more efficient system if the muscle were attached further from the joint, but that would be problematic for other reasons. You don't want to have like a muscle that goes from the shoulder out to here, because it's going to have to flex a very large distance. The big advantage of having the muscle attached close to the joint is that it only has to flex a little tiny bit to get a large motion in the actual lever arm. So that's really the trade-off. And this goes back to the F2 equals F1 times R1 over R2. You can have in fact, it might be more useful to look at this in terms of, again, R1 times F1 equals R2 times F2, assuming everything's perpendicular for now. You could have a small radius and a large force balancing out a large radius and a small force. So as long as your muscle is capable of applying a large amount of force, it only needs to move a tiny bit to get a weaker force to move a much larger distance. And this is always the trade-off. Anytime you're working with a lever, and also with ramps, pulleys, screws, inclined planes, any sort of simple machine, the trade-off is always distance versus force. You can take a large force acting over a very short distance, balancing out a small force acting over a long distance. And which one you want to actually use varies depending on the situation. Maybe you're able to apply a large force, but you only have a little bit of room to work with. Or maybe you have lots of space to work with, but you want to make it as easy as possible in terms of small amount of force. And by the way, what is distance times force? If you just look at it in terms of the units, what do you get if you multiply a distance times a force? If you think way back to 7a, force times distance traveled equals work. This is ultimately all about conservation of energy. A distance times a force is related to the amount of work you're doing. If you want to do something like lift an object up to a shelf, you can apply a lot of force for a short distance just by lifting it straight up, or maybe have a ramp and apply a weaker force over a much longer distance, but you're still doing overall the same amount of work. So this all goes back to conservation of energy. You can do that work by applying a large force over a short distance or by applying a small force over a long distance. You're still investing the same amount of potential energy. It's just a matter of how you want to break that up. So that's really the core of all of leverage, the whole idea of using a lever to do work. Any other questions on that? And I think that was it. Oh, there was also this one more question. If the person, sorry, yeah, go ahead.
What you were talking about work, and sorry, just so I can think of it like quantitatively, how are work and force related?
Specifically, work is the force applied times the distance traveled. Specifically, force parallel, that is force in the direction of travel times distance traveled.
Oh, so if you're pushing at an angle, only the parallel one to the, it's like if you're pushing a box at an angle, only the parallel component counts when you're calculating work?
Yeah, specifically the component parallel to the direction of travel.
Okay. Okay.
So if you've got a box sliding along the ground and you're pushing on it, let's say downwards and forwards, your force has a downwards component and a forwards component. The forwards component of your force times the distance traveled tells you the amount of work done.
Okay, thank you.
And presumably that's either doing work to increase the kinetic energy of the box, or maybe your work is just counteracting the work done by friction to keep it moving at a constant speed. But the idea of torque, radius times force, that radius is not distance traveled. It's distance from the pivot point out to the center. But if you have the object actually rotating, then the distance traveled is going to be the radius times the angle to get the arc length. So if you actually have an object that rotates some amount, you can take radius times force and multiply that by the angle as long as it's measured in radians. And that gives you the amount of work because you've got angle times radius. That tells you the arc length traveled multiplied by force, and that converts it to an amount of work as well. So as long as the object is all rotating through just one single angle, this formula, R1F1 equals R2F2, ultimately turns into conservation of energy anyway. In fact, it's entirely possible to work out the entirety of leverage, all this stuff about torque and levers and rotation and stuff. Instead of using the idea of torque, you could work it out with what's called, I think it's called potential work. I might not have the terminology right there. But basically looking at it in terms of if this object were to rotate a tiny angle, how much work would be done by each of those forces, and then assume that all those works balance out because of conservation of energy. So it's entirely possible to figure this out using this idea of tiny bit of work done if the object were to rotate very slightly instead of using torque. And it turns out to be the exact same equations, just a different way of getting there. Any other questions on that? Yes, if we wanted to draw the free body diagram, the extended force diagram, we would also want to draw in the force from the shoulder joint. We don't have to worry about it for torque, but if we do want to think of this as a complete force diagram, we've got the force from gravity, we've got the force from the muscle, and the force from the pivot should make all these add up to what?
0.
Yeah, so these should all add up to 0. So let's try this out. We got a force from gravity plus force from the muscle. We need a third force that makes all these add up to 0. So that's going to be completing the triangle. Force of gravity plus force of the muscle plus force of the pivot adds up to 0. Put these back at their assigned locations. Force of gravity, force of the muscle, and force of the pivot point. So those three forces add up to 0, as they should. So that would be the complete free body diagram, showing all the forces acting on the object.
Wait, sorry, how did you decide the direction of the force pivot?
That we want them to all add up to 0. So if you want some forces to add up to a certain value, you could just use the head to tail idea. That we have force of gravity plus the force of the muscle. And you can do this in either order. So if we add these, force of the muscle plus force of gravity, and we want to add in one more force that brings the total back to 0. So we add in one more that takes us back to the starting point, so that all three of these forces add up to 0.
Okay, that makes sense. But then just to clarify, the magnitudes are kind of an approximation because we don't have enough information.
Somewhat, yes. Although we did at least take care to make sure that these are roughly to scale with each other, that the tangential component of the muscle force is twice as much as the force of gravity. The only thing we're really approximating then is the radial component of the muscle force, because we don't really have an exact angle. So this is just a sketch, but I would say it's a pretty good sketch, because we're making everything to scale that we can. Any other questions on that one? And then this one's also asking, suppose the person's muscle suddenly goes completely limp, exerting essentially no force on the arm. So we are now getting rid of the muscle force completely. And that's going to change things. For one thing, the pivot force is now going to be different, because the pivot force is now just balancing out gravity, not balancing out the muscle force as well. But now we want to know what's going to happen 0.1 seconds after the muscle goes limp. So we now have unbalanced torques. We were previously assuming that all the torques add up to 0, but now we do have an unbalanced torque. And what happens to an object if the torques do not add up to 0?
There's acceleration.
Right, we get acceleration. Specifically, we can use the idea that the torque is proportional to the angular acceleration, alpha. Let me pull that out of the ether. Alpha. The torque is proportional to the angular acceleration. And what's the constant of proportionality there?
Moment of inertia.
Right, moment of inertia, I. And keep in mind this idea that torque equals moment of inertia times angular acceleration. This only applies if the moment of inertia does not change. If the object is changing shape, like moving mass further from the center or closer to the center, this doesn't really work. But assuming moment of inertia is constant, torque just equals moment of inertia times angular acceleration. And how do we define angular acceleration? What does that alpha actually mean?
Is it more than just like the delta lowercase omega?
Yeah, change in omega, specifically delta omega over delta time, how fast the angular velocity is changing. And if we want to know the rate at which it would be swinging, that is just delta omega. So how would we isolate delta omega here?
It should be delta omega times tau delta t over I.
Yeah, tau times delta time over moment of inertia. We have the torque. That was just the, or we could find the torque. That's just 80 newtons times the distance, 30 centimeters, or 0.3 meters. I think it would be a good idea to write that in meters here. Times the amount of time, 0.1 seconds. Do we have a moment of inertia here?
Did they give us, I guess we have an R, but did they give us an M above?
I don't think it gave, or it did give us a force. The weight of the force of gravity was 40 newtons. So we could divide that and find that the mass is 4 kilograms. But the problem is 30 centimeters isn't the length of the entire rod. 30 centimeters is just the distance from the pivot point to the center of mass. We might be able to approximate it as 30 centimeters times 4 kilograms. But the problem is that the shape of the object and how the mass is distributed actually matters here. That we can't just assume that this is a point mass located 30 centimeters from the pivot point. We would need to know more information about what actual shape this is. I mean, the arm you could probably just treat as a rod rotating around its own axis, or rotating around its own endpoint, I mean. But the problem is we don't really know how the mass is distributed. For instance, if you take a look at an actual arm, I would think you've got more mass in the upper arm than you do in the forearm because you've got more muscles in that region. So the mass is not evenly distributed, which makes it a more complicated calculation for the moment of inertia. So I think we can't really get an exact value for this unless we already knew the moment of inertia or knew something more about how the mass is distributed within the arm. We can at least say if we knew the moment of inertia, we'd use this formula to find the change in angular speed, how much it speeds up during that 0.1 second. But without more information, we can't really go any further.
What would the torque be?
What was that?
What would the torque be?
Torque, as usual, we can write as radius times force. So we take 30 centimeters, or in this case, I would convert that to meters, just because Newton meters is usually a better way of writing torque. So 0.3 meters times 40 newtons would be 12 Newton meters. And we don't need to worry about angle here because those really are perpendicular.
And we don't have to, because the pivot's not exerting a force because now, or no, there's no torque. The pivot doesn't have torque, so it doesn't matter.
Yeah, there is still a pivot force because the force, in this case, the arm is not falling off. So presumably the pivot is exerting an upward force to balance out gravity. But the arm is rotating because the pivot does not exert any torque. Any other questions on that? All right, then let's take a look at this other question with the, where was it? The capacitors. Looks like we've got a battery in a loop with a couple of resistors, and also a switch that links to another resistor and a capacitor. And we want to know immediately after the switch is closed, what's the current through each resistor. So let's say at this, at an instant that we'll call time 0, we close the switch. So these are now connected. Also, though, the capacitor is uncharged. And what can we treat an uncharged capacitor as acting like?
It's like a wire?
Yeah, uncharged capacitor acts like just wire, because if it's not charged yet, then it has 0 voltage. It's not exerting any pushback. So a truly uncharged capacitor we can treat as just wire for the moment. We can treat it as having 0 voltage, which means it doesn't really influence anything yet. So what we can now do is we can analyze what's going on in this simplified circuit, just treating it as a battery, a couple of resistors, another resistor in parallel, and no capacitor at all. And we can figure out the current everywhere there. So to find the currents, I would start by looking at the current through the battery. We've got this current going through the battery. Let me make that smaller. Current through the battery is also going to be the same as current going through which resistor?
So R1?
Yeah, those are all going to have the same current. But then when the current hits the junction, it's going to split. So we're going to split into, let's say, currents 2 and current 3. So we'll call these I1 and I2 and I3. And we want to figure out what is each of those currents at time 0 before the capacitor has any charge. Any thoughts on how we could find those currents? Yeah, R2 and R3 are definitely in parallel, because you can think of them as two paths that both start from the same high voltage, take different paths, and end at the same low voltage. So the R2 and R3 are definitely in parallel, which means how could we combine them? Yeah, add their inverses, 1 over R2 plus 1 over R3. That'll be 1 over 6 plus 1 over 3. 1/3 is the same as 2/6. So what do we get there? One over 6 plus 2 over 6 would be yeah, 3 over 6 is 1/2. And then we invert that again to find R equivalent. In other words, let's say R23. So the resistance of resistors 2 and 3 together is just 2 ohms. And once we've combined those, that's in series with R1. So what can we do with those resistances? Yeah, just add those together. 8 ohms plus another 2 ohms is 10 ohms. So this entire circuit altogether acts like just a single 10 ohm resistor. And if you've got a 42 volt battery and effectively a 10 ohm resistor, then how would you find the current?
You can say that epsilon equals negative IR.
Yeah. because we effectively just have, actually, I'd write it as epsilon plus negative IR equals 0, because we've got epsilon from the battery plus negative IR from that effectively one resistor. Those add up to 0. So I is going to be epsilon over R, 42 volts over 10 ohms, which is 4.2 amps. So that's the current through the battery, which is also the current through resistor 1. So we know resistor 1 has 4.2 amps of current at the beginning, before the capacitor charges at all. And how could we figure out how that splits up into I2 and I3? When we look back at the expanded circuit.
Wait, why isn't I1 just like 42 divided by 8? Why can't you just do that? Because it hasn't encountered the other resistors yet?
Current is really more about pulling it through the entire circuit, though. It's not like it's going to go faster here because it hasn't encountered any resistance yet. Like, we don't have infinite current through the battery because there's no resistance at all yet. The current through the battery is about the balance between how hard the battery is pushing versus how difficult it is to flow through all the rest of the circuit. I find it might be useful to think of the electrons in the wire as acting like a bicycle chain. Like, let's say you've got a pedals on a bicycle with a chain hooking it up to the gears on the wheel. If you turn the pedals, it's not like that segment of chain is easier to pull because it hasn't hit the wheel yet. You're not just pulling the chain links on the pedals, you're pulling on the entire chain at once. Same thing here. The battery is not just pushing on the electrons going through resistor 1. The battery is simultaneously pushing on all the electrons in the entire circuit. So the current through the battery is determined not just by the first resistor it hits, but by all the resistance in the entire circuit.
But then just to clarify, that would not be true for voltage.
For voltage?
Yeah.
Yeah, voltage is more about how much, it's more like the electrical version of pressure, how much pressure there is at each location. So as the current flows, it's gradually losing or gaining voltage. Or rather, each location in the wire can have different voltages. Except that any 2 points connected by just wire have to be at the same voltage. In fact, if we start looking at voltage, let's say we take a look at the voltage right before the battery, and we call that 0 as a reference point. Of course, that's not just that location, it's everywhere connected to that location by just wire. So all of these locations would be at 0 volts. So let's call this entire region 0 volts. Then you go through the battery, and what happens to voltage?
It goes up to 42.
Right. We gain plus 42 volts. So this location, this corner, is all at 42 volts.
I was just trying to remember, because I remember we went over a midterm question, one of the midterm 1 questions, and we talked about it like this. And so I was confusing current and voltage a little bit when you were talking just now, but I get it now, that why they're
Yeah, the way I think of it, current is really about a path. Like, this entire segment of wire is one path, so it all has the same current. But voltage changes anytime you cross over a circuit element, like a battery or a resistor or a non-empty capacitor. Whereas current only changes when you cross over a junction. Also, the resistor here, we know its resistance and its current. So what can you do with those values?
Calculate voltage?
Yeah, or rather delta voltage. We can figure out how much the voltage changes across that resistor. Current times resistance is negative 4.2 amps times 8 ohms. That's 24, what is that, 24? 32. plus another 1.6, 33.6, I think. So that would be how much voltage we're losing as we cross over that resistor. We started with 42, we lose 33.6, so how much is left?
Like 8.4?
Right. So that would be the remaining voltage afterwards. We could say that this next zone, this region over here, again, following wire until we actually run into something else. This zone is all at 8.4 volts.
So current splits and divides, but voltage doesn't. And that's from the junction rule?
Right. Because current is all about flow, how many electrons per second, or how many coulombs of charge per second. But voltage isn't about flow. Voltage is about how much push there is in that region, how much energy the electrons have in that region. So this region has 8.4 volts of electrical push, whereas a path can have a certain amount of flow in terms of charge per second flowing past that point. And now that we know the voltage everywhere, we can use that to figure out the currents as well. Because we know, for instance, that let's say resistor 3 is a jump from 8.4 volts to 0 volts. So subtract final minus initial to find the delta voltage. And then, as usual, delta V equals negative IR. So divide by resistance to get the current. 8.4 is the difference. Divide that by 3, and that tells you the current. And also for resistor 2, we know we're starting at 8.4 and ending at 0. So that same delta voltage, because they're in parallel, divided by 6 ohms tells you the current through resistor 2. So that'll be the current in each part of the circuit. Any other questions on that? And then how would you expect these to change as the capacitor gradually fills up?
Current will decrease to 0.
Which one specifically is going to decrease to 0?
You mean like I1, I2, or I3?
Yeah, because they're not all going to decrease to 0.
I3 will, because technically, because they're in parallel, the I2 one will still keep going.
Yeah, because as the capacitor fills up, I3 gradually approaches 0, because as the capacitor fills up, there's going to be less and less current. Eventually, when the capacitor is full, there's no current at all in that branch. But the important thing here is, because of that arrangement of parallel networks, there is still a path that current can take. In fact, you could even figure out how much current there is after a long time by just saying, well, after a long time, there's no more current at all through this branch. So we can ignore that. And what's left is just a single loop. So you can just add together those resistors as if they're in series, because once that other branch is cut off, these are in series. Treat that as just 14 ohms. So 42 volts divided by 14 ohms tells you the final current in this loop. And then you can compare that to the original currents and figure out, are these currents getting weaker or stronger as time passes? And then for a graph, we can assume that each one of these currents is exponentially changing to approach the asymptote. They're just going to have different asymptotes. Or I guess I1 and I2 are going to be approaching the same asymptote, whereas I3 is approaching 0.
Would we be expected to calculate that asymptote for I1 and I2?
Yeah, for I1 and I2, you can just figure out what's the final current by saying, well, you still got 42 volts from the battery, and these two resistors together in series are 14 ohms. So you could just take 42 divided by 14, that's 3, I think. So the final current is going to be 3 amps in that loop.
Oh, right.
So the I1 starts at 4.2 and approaches 3 from above. R2 starts as some lower value, I think, what is that, 1/3 of 4.2, and approaches 3 from below. And then if you wanted to find the final charge on the capacitor, assuming the capacitor is full, this branch with R3 and the capacitor is in parallel with R2. So if you can figure out the final voltage on R2, that's the same as the final voltage on the capacitor. And then you could use the usual equation, delta V capacitor equals Q over C. You know the capacitance. The voltage is going to be the same as the final voltage on R2, and then you can solve for charge. Any other questions on that?
Wait, isn't the final voltage on R2 0, though, right?
R2 is going to have current flowing because there's still a loop present. The final voltage on R3 is going to be 0 because there's no more current through that path. But there is still current through battery R1 and R2 because those still form an unbroken loop.
So to solve that, so what is delta V capacitor then?
Delta V capacitor is charge over capacitance. But because the capacitor branch is in parallel with R2, that means in the end, capacitor is going to have the same voltage as R2. So you can find the final voltage of R2 by multiplying the final current, which we found was 3, times 6 ohms. 3 amps times 6 ohms would be 18 volts. So in the end, R2 has 18 volts. That means the capacitor is also going to be at 18 volts because they're in parallel.
And it has to be the same amount because there's no current going through that after a long time?
No current going through means we can ignore R3. Because technically we would say the voltage of R2 is the same as the voltage in R3 and the capacitor combined. But if R3 is getting no current, then it's got no voltage.
Only initially though, right? Only initially is
finally, not initially. In the initial situation is the capacitor has no voltage and all the voltage goes to the resistor, causing current to flow. The final situation is there's no current flowing, so the resistor has no voltage. Instead, the capacitor has lots of voltage because it's got lots of charge.
Okay, I think that makes sense. I'm just a little confused numerically on the delta V capacitor. Like we have enough values to solve it, correct?
Yeah, because the final voltage of the capacitor is the same as the final voltage of R2, which was 18 volts because we have resistance times current. So you set that equal to charge over capacitance, multiplied by capacitance, and you've got the charge.
And they have to be equal because they're in parallel.
Yeah, assuming we're ignoring R3 because R3 no longer has any current flowing through it anyway.
Okay, I think that makes sense. And it has to be equal because otherwise there would be some sort of current flowing if there is current flowing, then R3 is going to have a voltage of its own. But if we're assuming the capacitor has filled up completely, then that means there's no more current flowing through that branch. Anyway, I've got to get going, but I'm going to be in office hours throughout the day, Tuesday and Wednesday as well, if you want to go over more examples of this. You can find the link and schedule on math.nchoose.org. So good luck on finals. You're welcome. And I will see you next time.